Well, let's see. Let's get on with the lesson. Last day, we started talking about taxonomy, and we looked at classification schemes, starting with Democritus, which was very forward-looking, and then the backtracking of Aristotle. And I'd like to go further. We started with just the 7 metals and carbon plus sulfur. It was a point of departure for Democritus. And the Aristotelian view held for a long time, but eventually it started to crumble in the light of more data. And again, all of these slides that I'm showing, I'll convert to PDF and it'll be posted at the website, so you can just watch, take notes, but you don't have to copy every last detail down. So by the time of the American Revolution, these are the elements that were known. And here we have the arsenic, antimony, and bismuth, 3 delightful elements that were given us in the 12th, 13th, and 14th centuries by the alchemists. In 13th century India, they knew how to isolate metallic zinc. In fact, there's a pillar there of high purity zinc that stood for the duration. It's almost 1,000 years now, and it's in high purity. Platinum was unknown until the Spanish came to South America. It's unknown. It's an American metal. Platinum is an American metal. And oddly enough, it was given a bad name. Plata is silver. So platina is like a diminutive of silver. But we now know that platinum is far superior to silver. It's far more noble, has a higher melting point, higher chemical inertness. Fantastic metal, American metal. And then all of a sudden we have discovered. What does this mean? Well, are we saying that until 1774 there was no oxygen because it was discovered then? No, what does it mean? It means it was isolated and characterized. Isolated and characterized. So Lavoisier characterized oxygen. Cavendish characterized hydrogen. And so now we see the shift from craft to science. Right? So now we've got all this data, and this Aristotelian model is looking goofier and goofier. So we need to have some better explanation. And one of the earliest was that of John Dalton. John Dalton was an Englishman who proposed the following classification of the elements. John Dalton's science was very accurately weighing the elements. So he's arranged the elements here in a column. It's a double column, but it's only made double for convenience. As you can see, it starts with hydrogen and goes to mercury in ascending order of atomic mass. And he was very proficient at measuring atomic mass. And furthermore, he started to abbreviate. Instead of writing gold, he made this symbol. Silver was S with a circle. He could have worked on a ranch out in the West, couldn't he? This looks like branding things, aren't they? Well, this is interesting, cute fonts, but in point of fact, they were short-lived. Berzelius, the Swedish chemist, suggested that the French might take umbrage at having to use I for iron. So he said, why don't we choose something neutral? Let's choose Latin, the language of scholarship. And so iron became Fe for ferrum, and lead became Pb for plumbum, and gold is Au for aurum, and so on. And nobody quibbles because nobody speaks Latin, so it's neutral for everybody. Okay? John Dalton also talked about other things. He said, I'm going to propose a model. And this is right out of the text, out of chapter 1 of the text, 1803. And these are the planks of his model. That matter is composed of atoms that are indivisible and indestructible. Well, doesn't that sound an awful lot like Democritus? He's taking us back. He's getting us out of that Aristotelian rut and moving us back to something that makes more sense. All atoms of an element are identical. That's good. Atoms of different elements have different weights and different chemical properties. Well, this is important. The word property is really important to connect the concept of property with something fundamental in the makeup, in the constitution. Right? So what I'm doing is, listen to me, I'm talking at 2 levels here. I'm talking at the level of this is Dalton's model, but then there's a meta-knowledge here of how you develop models in general. If you're trying to model, I don't know, the efficacy of a particular drug, these are the baby steps that you'll go through. Atoms of different elements combine in simple whole number ratios to form compounds. That's important. That elements, because they are the building blocks, they combine in whole number multiples. If you have a set of blocks, mechanical, physical blocks, and I tell you to build something, and I say, oh, by the way, you have to cut the blocks in smaller pieces, you're going to get angry, aren't you? You're going to say, well, I thought these were the blocks. So these are the basic blocks. So therefore, whole number ratios is a consequence of that. And lastly, this is Democritus, that the being is made of particles that are eternal. This is eternity here. Atoms cannot be created or destroyed. And when a compound is decomposed, the atoms are recovered unchanged. This is good stuff. It's 200 years ago. It was just last fall that there was some events in the world celebrating the bicentennial of Dalton's scientific achievements. There were other classes. Just to let you know, these scientists of that era, they were polymaths. They weren't specialists. You know, I'm specialist of atoms that are left-handed on Thursday afternoons and don't talk to me about anything else. These people had broad scientific interests. Dalton did a lot of work on vision. He, like many men, was afflicted with red-green color blindness. And he developed the understanding of red-green color blindness, and it is known as Daltonism. Same man. Other classifications, Dobereiner and Jena, talked about triads. People remember, they were measuring atomic masses. So he saw that if you take the atomic mass of chlorine, add it to the atomic mass of iodine, divide by 2, you get something that's really close to the atomic mass of bromine. And he did it for other triads, and he found that the middle member of the triad had an atomic mass that was midway between the atomic masses of the end members. An attempt. Got to give him credit. Second was Newland's that I'll talk about. I like Newland's because he had a musical flair about him. He talked about octaves. He said, look at sodium. Magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, potassium. 1, 2, 3, 4, 5, 6, 7, 8. Potassium lies 1 octave from sodium. So he talked about octaves. When he presented his results at the sitting of the Royal Society, he was ridiculed, he was laughed at, he was derided. Somebody rose and asked him if he had considered putting the elements in alphabetical order. They were very cruel. You know, these people were nasty. They don't welcome innovation. Science is very hostile to innovation when it challenges existing theory. Sort of like management, you know, same thing. So let's move on to something that really took the giant step ahead, and that was Mendeleyev. And I also want to mention Lothar Meyer in Tübingen, who came up with the same classification scheme, but we're going to see in a moment why Meyer is not well celebrated today, and the glory goes to Mendeleyev. 1869, Mendeleyev. Here's a picture of him taken from that period. He was 35 years old at the time he enunciated this. 35. Positively brilliant. Here's his paper. It was published in the Journal of Russian Chemical Society, 1869. And it's really great because he actually goes through the thought process for you and describes. I need to give you one piece of background. Mendeleev played cards.